I'm going to continue doing these spring dropping experiments with different springs, different objects, different masses, different velocities. So I have 4 different springs here. In the first one I've used this one. I got 4 different sizes, and I'm going to start with the smallest one. This is going to be a small scale spring dropping experiment. So with a wooden stick, I can place it over the wooden stick, and this time with wooden balls, and I can just slide it over and let it drop. And this is going to be the one mass, and then just add another one for a 2 mass. Okay, well, I taped them together, and then 2 on top for the 4 mass. So I'm going to do 1 mass going 1 velocity, or 1 mass drop from 1 height, then from 4 times the height, then the 2 mass drop from 1 height, and the 4 mass drop from 1 height. Now, what I'm going to do each time is measure the spring when it is uncompressed, the total length of the spring in an uncompressed state, then measuring the length of the spring when the object is resting on it, when the object is resting on the spring, so the static compression, and then when you drop it, the compression that produces is called the dynamic compression. So we have 3 different compressions: the static compression, the dynamic compression, and the total compression. So again, the static compression is the compression when the object is resting on the spring. The static compression is the compression produced when it is dropped. So that's the dropping energy, and that's what we want to know. And then we have the total compression, which is the static compression plus the dynamic compression. Okay, so what we want to know is the dynamic compression. So only the energy, the dropping energy. So what we have to do is we have to do the total compression minus the static compression to know because we only want to know the dynamic compression. Okay, so I came to the conclusion that for this spring and for these light weighted objects, there is no static compression. So now normally what should happen is the one mass going twice as fast should produce exactly the same spring compression as the 4 mass going 1 velocity. So let's find out. Now let's discuss the results. So once again, the length of the spring uncompressed is 1.9 centimeters. For the one mass, one velocity, I had a consistent compression of 0.3 centimeters. When we double the velocity of the one mass, I had a very consistent compression of 0.6 centimeters. And again, both parties agree that when we have the same mass but we double the velocity, we get twice the spring compression, and I have exactly these results, 0.3, 0.6. Now, when we double the mass, two mass, one velocity, I had a very consistent compression of 0.4 centimeters. This is once again where the trouble arises. One mass, two velocity, two mass, one velocity. They both have the same compression. However, they don't have the same, they both have the same momentum. However, they don't have the same compression. So once again, according to draft science, they both have the same energy. So they both are supposed to have the same compression. According to conventional science, the prediction is, well, here's some explanation. The compression x is proportional to the square root of the mass m. So if the mass is doubled, the compression increases by the square root of 2. And so we have to multiply the one mass, one velocity with the square root of 2 to know the compression of the two mass, one velocity. If we triple the mass, we have to multiply the initial compression with the square root of 3. If we quadruple the mass, we have to multiply the initial compression with the square root of 4, etc., etc., etc. So the initial compression is 0.3, and the square root of 2 is 1.41. See, hold on. So again, the square root of 2 is 1.41 times 0.3 times the initial compression, which gives us 0.42. My result is for the two mass, one velocity, 0.4, and the prediction is 0.42, which is very close, of course. Now, of course, on the ruler, it's from the perspective of the camera lens, it's very difficult to see smaller decimal numbers. So 0.4 is the best I could see, but still extremely close to the prediction. Then for the 4 mass, one velocity, I had a very consistent result of 0.6 centimeters. The prediction is the square root of 4 times the initial compression. So the square root of 4, which is 2, of course, times 0.3, which is 0.6, of course. There we go. So, which means that the one mass, two velocity gives exactly the same compression as the 4 mass going one velocity. And so all of my results are perfectly in line with the prediction of conventional science. Now, draft science will, of course, say that, well, I'm only measuring millimeters. The differences are so small. It's only a difference of 3 millimeter and 2 millimeter. We want to see bigger differences. Well, hold on. I have different springs. This one being the longest one, the largest one. And so I can try out heavy masses, and so there will be bigger differences. And that will come up in the future. There we go.